I'm good with this, that's fine. But you don't lose all your.
No.
I'm noticing a number of people making careless errors. The process is pretty much spot on, but a lot of careless errors. And the lesson from a teacher's point of view is, please show your work. Got too many students will just give me an answer in the end. And when it's just a simple little brain burp that happened. So instead of having everything taken off, you just have a tiny little deduction. So anyway, it's 31.3, I believe, 31.3 meters per second. So where you set height is equal to 0, whatever you set it to, there's some initial height and the final height is 50 meters below that. So if 0 is here, this is 50. If 0 is down here, well, that's 20 and 70. The big thing is that the final height is 50 meters below whatever your initial height is. If you made this 10, if you made 0 right here, and that's 10 meters, well, this would be negative 40 meters. So whatever that is, minus 50 gets you this. I think a number of people were sticking with 0 at the ground. Nothing wrong with that. So this becomes 5 times 9.8 times 70, which was 3430. So my total is 3,430 joules.
Okay.
And so in the end, this is 5 times 9.8 times 20. So if that's 70, this is 20. And that was 960, 980. So I have 3,430 joules total, of which 980 joules is potential energy, so kinetic has to be whatever's left over.
34, oh, sorry.
Go ahead.
No.
Sure doesn't matter what height you use, you're still gonna get the
We
same
got
answer.
24.
Yeah.
Okay, I was so confused about that, yeah.
Just so long as the final height is 50 meters below the initial height.
So why do I feel like I had to be doing so much more than what I was doing? Cause that looked so simple.
That's physics physics in a nutshell. Okay, maybe not.
I'm just.
So once you have the amount of kinetic energy in the end, so no matter what, as long as, again, final height is 50 meters below the initial height, you should get 2450 joules for the kinetic, unless I made a careless math error, and that's equal to 1/2 times mv squared, so 1/2 5 times v squared, and final. And so 2450, and then interestingly, 1/2 times 5 is 2.5. There are a couple of people who, at that point, decided to do all the more complicated stuff fine, but then get to the simpler one and said, you know, it's time to make a mistake somewhere.
Oh, wait, so you still doing something? What you doing now?
Yeah, well, actually, let's solve it for v. So divide by 2.5. And 1960. Okay, I got a nod over there. That's equal to v final squared. Oh, no, not 980.
It's 980.
I'm gonna say, hold on.
And so VF is the square root of that, which is 31.3 meters per second.
So if we have a problem like this, and the height is like that, instead of trying to figure out what the height is, we could just do 70 for the initial height and 20 for the final height.
Yep.
Always.
You can always make the ground 0.
Okay.
Because in this case right here, when you're using MGH, yeah, the height is 0 at the ground, it works. We will, before we leave today, deal with a situation where you don't want that. But we won't be dealing with MGH at that point. All right, I think we need to sort of stretch our legs, become refreshed. I'm gonna pause the video and I'm gonna pretend that I'm gonna remember to turn it back on. And we're rolling. Time for the ski slope problem. It's gonna look far more complicated than the previous two problems, but it is not. All right. We have a skier at the top of a hill. Or a snowboarder, whatever you happen to be riding. Starting out 100 meters below wherever down there is. I want to know, first off, how fast is the skier going at the bottom of the hill? All right, so obviously we've got additional forces involved. Last time we just had a gravitational force acting down, and that was really nice because that's number one on the list of conservative forces. The classic reason, one of the reasons why we do ski slopes in physics is because the friction is low. And so we're just going to go ahead and take that next step, and I'm going to say that it is frictionless. So I'm letting the coefficient of kinetic friction equal the coefficient of static friction is 0. So it's a frictionless surface. All you've missed, Latoya, is the fact that I'm going to make a much more complicated looking problem, but it's not as complicated as it seems.
All right. Go ahead and show that.
Skier on a frictionless slope. So I want to take a look at the skier when the skier is at this point right here. Because we do need to figure out what forces are acting on him, because we have to figure out the forces to figure out if they're conservative forces or in conservative work, or non-conservative forces, non-conservative work. So at that point right there, what are the forces acting on the skier?
Weight.
Okay? Anything else?
Friction.
Pardon?
Friction.
Making it frictionless. But if you want to make it more complicated, we can.
No, we're good.
All right, so weight, conservative or non-conservative?
Conservative.
Normal force, conservative or non-conservative?
Don't know. I think it's conservative.
Or the other one?
Non-conservative.
Oh, there you go, non-conservative. Yeah, normal force is a non-conservative force. Remember that normal force is just a push. If I push a box, it's not like I have the ability to create conservation of energy. I'm putting energy into something when I move it.
So is that the letter, and is that 3?
We're not sure where up here?
Yeah.
That's a mu
Yeah.
sub s
S.
and a mu sub k. This is the coefficient of static friction, coefficient of kinetic friction. This whole bit is just shorthand for saying it's frictionless. No friction at all. Because physicists hate writing out words when you can just do it in some letters.
I know.
Because writing words has nothing to do with writing letters.
You said static friction or what friction?
Kinetic. All right, so obviously I don't have to worry about the weight because we just dealt with a whole bunch of problems with weight involved, so that's not potentially an issue. Normal force is potentially the issue because it is non-conservative. So this goes back to that whole bit of 3 examples. If I have a box that is moving to the right, and I push on it in the direction it's going, is my work positive, negative, or 0?
Positive?
It is. Work is positive. If I have a box and it's going to the right, and I'm pushing against the direction of movement, positive, negative, or 0 work?
Negative?
I have a box that is moving to the right, and I'm pushing it down and to the left. Work is still negative, because part of the force is opposing it. I have a box that is going to the right, and I'm pushing straight down on it. 0. Because this force is not pushing in the direction, there's none of it pushing in the direction of movement or against the direction of movement. Over here, normal force is perpendicular to the surface. That's why it's called normal. In which direction is he moving at this point?
Down, right?
Thank you. Just saying down means that way. So he's moving in that direction. The normal force is in that direction. Matter of fact, no matter where he is, the normal force is always perpendicular to the direction he is moving. Therefore, what is the work done by the normal force?
0?
So there is a non-conservative force here, but it's not doing any work. So since the only force doing anything is weight, try that wording again. Since there's only one force doing any work, and that force is conservative, energy is conserved. Sort of work by the normal force is 0 joules, because normal force is perpendicular to basically the displacement. And I should say instantaneous displacement, because that's what matters here. I'm not worried about overall displacement, I'm talking about displacement. While the normal force is in that direction, he's moving that way. When he's here, the normal force is this way and he's moving that way. So no matter where he is, the normal force is always perpendicular to where he's moving. So this is a conservation of energy problem. We're going to do the exact same thing we did before, just we have different numbers. Matter of fact, I didn't give you a mass for him. We don't need it. It's not going to change the answer. So if I don't give you a mass, it means one of two things. It means one, I either forgot to and I meant to, or you don't need it. On a quiz or test, if I don't give it to you and you're not sure which one of those is, you come up and ask. And my reaction, probably one of several things, it's, oh, it's fine. And then I have a puzzled look on my face and then I work something out and I go, oh. And I announce it right on the board and I announce that there's a mistake there. Or I go, nope, you don't need it. If you don't need the mass, you can make up any number that you want as long as it makes some sense. Don't pick 0. And don't pick a negative number. Although a negative number would still come out with the right answer. So, we start out with, well, we have kinetic and we have potential. We're going to end up with kinetic and potential. Shocking. I am making the assumption that he's not bursting into flames as he goes down, that there's no change in the rest energy. To simplify it a little bit more, he's just delicately balanced right there on the top of that slope there. A gnat lands on his back, which is just enough to get him start to move. In other words, his initial speed is approximately 0 meters per second. So what is his initial kinetic energy?
0 meters per second, or 0 joules.
There we go. So 1/2 times whatever his mass is times 0 squared is 0 joules. His initial potential energy. What formula are we going to use for potential energy here?
MGH,
Why?
because that's what Latoya's been saying.
Okay. I guess I never asked her why. Why, Latoya?
That's acceleration due to gravity.
What about it?
I don't know, mister.
So close. Anyone else want to fill in the gaps?
That's what I said, so.
Oh, not.
No, but seriously, it has to do with our weight though, just in where we are at that point of time on Earth.
Yeah, all right, so sort of filling in some gaps there. MGH is the formula associated with mg. If the acceleration of gravity is relatively constant, so you're near the surface of the planet, and to the point where the force due to gravity we call weight, then the formula associated with that is mgh. That's what I was looking for as far as y goes, not a full derivation of it.
Associated with weight.
Yeah, so each conservative force has an associated potential energy formula. So the one associated with the weight is mgh.
So is there another formula associated with?
There's another formula if we're dealing with the generalized gravitational formula. Chapter 9. And I said that we were gonna do a problem using the negative g and 1 and 2 over r, and I just realized, should have hit earlier, that's chapter 9, we'll deal with that. So sort of a teaser there to make you keep coming back.
No.
So mgh, so my mass is m times 9.8. What's my initial height?
100 meters.
All right, it has now been established. What did Rebecca just establish when she said that was 100 meters initially?
The ground is 0.
Because Rebecca said so. Now, are you comfortable enough to just leave it in there, or do you want to stick a number in?
I want to stick a number.
What number do you want to stick in?
5.
Okay. 5 kilograms. So it's going to 4,900?
Yep.
Yeah, that's right.
So, a 5 kilogram person? Basically, it's a newborn. You could put a newborn on the ski slope, would you? What's my total in energy initially?
49.
What's my total energy at the end? Yep. Because energy is conserved here. What's my final potential energy?
Is it 0?
Why?
The ground is 0.
Yes,
Yeah.
established in the beginning. So, therefore, what's my total kinetic energy at the bottom?
4,900.
Yeah, no, I don't like this one. So something else is gonna be happening.
We'll throw a spring into it in just a moment.
Wait a minute.
All right, so 4,900 joules here, that's gonna be equal to 1/2 times R5 times RV squared. Divide by 2.5, divide by 2.5. Somewhere around 200, I'm gonna guess
I got
What?
1960,
1960?
I think, yeah.
1960, 100 is 44.
1960.
44.27.
finish it off?
I want a meters per second.
Municipal.
Thank you. That was the international symbol for all of the units. All right, so we have how fast he's going at the bottom. Questions up to here because I'm going to change the problem slightly.
And that's because you squared it, right?
Square rooted it.
Okay.
Yeah, if you don't have a calculator with you right now, or you're not using the calculator right now, just when you get home, I do recommend going over the notes, just making sure you get the same numbers. All right. So, he enjoyed it so much he decides to go back up to the top. Little did he realize there was a cave in.
Poor baby.
He's the one who did it. Now, if you're concerned for the safety of this infant, at the bottom down here are clouds, kittens, and cotton balls. Kittens we don't hurt. If they've been cats, they could have been squashed, but kittens, no. I've asked this before, I'm sure, but who are the cat people in here? I assume everyone else is a dog person.
What if you're both?
I was about to say, I don't really, I'm from.
What else?
Yeah, dogs and cats.
Yeah.
All right, so as he comes down, right when he hits the cotton balls, clouds, and kitten, or doesn't hit the kittens, cotton balls and clouds, kittens are there just to help him. How fast is he going right when he hits, or right before he hits?
Is it gonna be, below 0, like the height?
I assume it's the same height as the
Oh,
beginning.
never mind. Okay.
You know, I've done this bit for years now, and I always have him hitting cotton balls, clouds, and kittens, or cotton balls and clouds and kittens are there. I don't think I've ever actually mentioned the fact that there's gotta be snow down there too, if there was a cave in. So there's snow